This is section 3.1 day 2 video, and so I just want to remind you that we're starting to look at derivatives. So when I say derivative, hopefully you're thinking slope, and so when I say slope, hopefully then you think derivative. So we're going to use those two words pretty interchangeably, and so when we talk about derivative or slope, we're talking about that of a tangent line. And so we can calculate the derivative as opposed to actually finding the derivative by hand, which we will do a little later in this chapter. But for now, we're just going to calculate the derivative, and to do that, we're going to use our Math 8 key. And so on our calculator. So let's just try this. So for the function x squared, if we want to take the derivative of function x squared with respect to x, that would be 2x, that would be, and then evaluate that at 0, our calculator is going to give us a value of 0. So go ahead and work on the calculator, do a Math 8, this will pop up, and then you can plug in your information. Your x squared is your function, we're evaluating it at 0, so 0 goes here, and then if you have an older Texas instrument like an 83 or an 84, you have this syntax that's a little more programming look, and n-deriv means numeric derivative of function x squared, and then they have a comma with respect to x, and comma evaluated at 0, and then you put in a right bracket. When you hit enter, you also get that value 0. So this is for the newer calculators, this is for the older calculators. So let's talk about then a second way to calculate the derivative, and this is inside your grapher. And so in y1, we're going to put this function, and go ahead and enter this function, and then go ahead in y1 get a window from -1 to +9, and then from maybe like -0.5 to +6.5. Why don't we try that? So go ahead and pause this video and get that on your screen. Okay, so you should have that function in y1 and this on your screen. And now we're going to calculate the derivative right inside the grapher. So right now you're in the grapher, you're in the screen. Under the Calc button, you're going to choose option 6. So you're going to do second Calc 6, and then option 6 is a dy dx calculator. Okay, and so we're going to do second y6, and then we're going to type in the location of 0. And when you type in the location of 0, you should get a value of 4. And when you type in the location of x equals 1, so second Calc 6, and then type in a location of x equal to 1, and you should get a value in your derivative 1.667. And then we're going to type in a value of 2, and at the value, so second Calc 6, and then x equal 2, and you can get a value of 0. And then when we do an x equals 3, we get a value of -1. When x equals 4, we get a value of -1 1/3. When we do an x value of 5, we get a value of -1. When we do an x value of 6, we get a value of 0 again. When we do an x value of 7, we're going to get a derivative of 1.667. When we do an x value of 8, we'll get a derivative value of 4. And so, so those are the values of the derivative at each one of those values of x. And notice that, that again, I say derivative, you're thinking slope. So if we go back up to the top of the table here, when x is equal to 0, the slope of the graph is 4. When x is equal to 1, the slope is 1 2/3, or 1.6 repeating. When we're at x equals 2, the slope of the graph, or the tangent to the graph, is 0. It's flat. It's just not showing up here, and so on and so forth. So these are all the slopes of that curve. So the curve starts out sloping upward or sloping positive, and then it goes over a hill where it slopes 0, and then it starts decreasing again where it's sloping negative, and then it hits a valley where its slope is 0, and then it starts to increase again where it's sloping up positive. So from last class, we know that a function is differentiable if it has a derivative everywhere in its domain. So that last function was differentiable everywhere. So what we do is to kind of see that visually, we need to have continuity and smoothness. So if we have a continuous smooth graph, we know it's differentiable everywhere. That's kind of the visual. No jumps, no holes, no asymptotes, and smooth. No cusps, no corners. So if we have continuous and smooth, we know it's differentiable everywhere. And if they're on closed intervals, so if we're just looking at a portion of the domain, then we can have a one-sided derivative at the endpoint. So sometimes then, as we're looking at this definition of derivative, sometimes functions have specific points where this fails to exist. You know, so sometimes a function will have a jump, or a hole, or an asymptote, or a cusp, or a corner, and that's when the derivative fails to exist. So, so we're going to go back to our world's longest piecewise function that we put up in class, and we're going to look at those situations. So we know that continuous means the left and the right limit are equal. In other words, we are always trending, if we look on either side of that point, we are always trending towards the same y value. And so, and that's kind of what that says there. And that's kind of the math notation for what this says. And for smooth, then we know that we're talking about the derivatives are the same. So we have to have that, the left derivative and the right derivative being the same. So when we talk about that scenario then, let's talk a little bit about the derivatives. So when we talk about a right-hand derivative and a left-hand derivative, we're looking at that smoothness. So approaching from the bigger values and approaching from the smaller values. So if we look at our world's longest piecewise function, which I realize that you can't do in this video, but we're going to look and see whether our derivative exists at specific locations. So we're going to do our second card for this piecewise function. And so we already have a card that talks about the limits and continuity. So now we're going to have a card here that talks about derivatives. So we're gonna get a card, and it has a location on the function, and you're going to have to compare the left-hand derivative and the right-hand derivative when x is equal to 0. So you'll know the functions that are coming together, and you'll have to do an n-deriv, a numerical deriv on your calculator. So you're going to have to do a math 8 to find the derivative values on either side of 0. And as you can see, from x equals 0, we don't have the same derivative values. So the function is continuous. We don't have to lift our pencil at 0. We can draw right through 0 without lifting our pencil. But if our derivatives are different, that means we have like a cusp there, a sharp turn. So since the left-hand and the right-hand derivatives are not equal, then the function is not differentiable at that location. So that's kind of how the activity is going to go. So as you get back into the classroom, you know, make sure to ask me some questions about those cards if you didn't participate in that activity. So at this point, then, you should be able to work on day 2 of the homework for section 3.1. And just to kind of summarize section 3.1 in general, we know that our essential question was, what does the derivative represent? We know it represents the slope of the curve, or more specifically, the slope of the tangent to the curve. But we kind of shorten up that statement just by saying the slope of the curve. So again, you can start that day 2 homework, and this is the end of section 3.1. So if you're going to do a proficiency quiz in lieu of the homework, you can do that as well.